Okay, Section 8, decision analysis. So, rules of thumb, intuition, tradition, simple financial analysis are often no longer sufficient for addressing common decisions such as make versus buy, facility site selection, process redesign. In general, the forces of competition are imposing a need for more efficient decision making at all levels in an organization. So, decision analysis is the discipline of evaluating complex alternatives in terms of values and uncertainty. Values are generally expressed monetarily because this is the major concern for management and business. Furthermore, decision analysis provides insight into how the defined alternatives differ from one another and then generates suggestions for new and improved alternatives. Numbers quantify subjective values and uncertainties, which enable us to kind of understand the decision situation that we're trying to accomplish. So, a couple of key terms are going to be important for us. Acts are controllable. These are the choices that we make. We decide to act in one direction or another. The outcomes, after we've made that decision, what actually happens is a state of nature. These are the events that we do not control, right? I decide to go get groceries in my car. That's a choice I made. I didn't decide that I was going to get hit in a car accident on the way there, right? So those are the states of nature, the things that are uncontrollable for me. All possible outcomes must be listed. Again, completely exhaustive and be mutually exclusive. They can only belong to one category. A payoff table will list all possible outcomes associated with each act and the various states of nature. Okay, so again, when considering states of nature, the outcomes, it is possible to foresee what the outcomes might be, but we simply do not have direct control of those outcomes. That's kind of the important piece there. Here's an example. This is a payoff and opportunity loss table. The consequences resulting from a specific combination of acts or decisions that we make and the states of nature will produce a payoff. Payoffs can be expressed in like profits, time, cost, distance, really anything that's kind of an appropriate measure. All right. The opportunity loss table can also be referred to as a regret table. The opportunity loss will have a positive number, but just know that it is a bad thing, right? These are the losses. So you'll notice too from a profitability table, we'll have the maximum expected value will also correspond to the lowest opportunity loss. Okay, and that's how these tables work out. So in this case, we're looking for if the the interest rates increase from zero, if they stay the same, or decrease if we invested in this company, this bond, and the individual stocks, the different returns that we would expect to get. Okay, so here are the decisions that we make. Here are the outcomes, the states of nature that we do not control, and then here are the outcomes. All right. In a decision tree, the expected monetary value, the MV, is the average payoff that we would expect if the exact same event were repeated a large number of times. This is where we get into like normal distribution, right? Where if this occurred over and over and over again, we would expect this outcome to happen, say, 60% of the time out of the 100 events. All right. So, a couple of things to remember: the probabilities are assigned to states of nature, not to actions. We don't assign probabilities to a decision that we make. Hey, there's a 100% chance we'll decide this or decide that. No, we assign probabilities to the events, to the states of nature only, the probability of the outcome of that. All right. Also, the expected monetary value will differ from the figures in the payoff table, as the expected monetary value is essentially a weighted average of the outcome. So we would not expect it to exactly equal the items in the payoff table. It's going to be an average of items. All right. And then the last item here, the expected opportunity loss, is computed the same way. We multiply the opportunity loss by the assigned probability. The opportunity loss, um, the expected opportunity loss, also called regret results, compare decision outcome with what might have happened. Therefore, it depends upon the feedback available to decision makers as to which outcome the alternative option would have yielded. Okay. The typical process for us is step one, we assign monetary values to the impact from the probability table. We assign a probability, sometimes subjectively. Hey, there's a 60% chance we're going to earn this business. There's a 10% chance that, our truck carrying this item is going to get into an accident, those kinds of things. And then we simply multiply the probability by the monetary value and we add them together, and that's going to get our expected monetary value. Okay, here's how it looks. So let's say that we have a new product design, we can enhance an existing product, or we can do nothing. Well, to design a new product is going to cost $10 million, and there is a 65% chance if this new product design that there'll be strong demand. This will result in $25 million in gain. Well, we take the 65% chance of $25 million plus the 35% chance of losing $5 million, and we get to a $4.5 million outcome, the expected monetary value. We do the exact same thing for enhancing. It only costs us $3 million. There's an 80% chance of strong demand because we know demand already exists versus a new product altogether. So 80% times the 10 million. And then if there's weak demand, we still get a 20% chance of 5 million, right? Minus our initial investment, we get to a total of $6 million. And so from this, we choose the largest expected monetary value for us, okay? The expected payoff from perfect information. This is saying, listen, how much would we pay? What additional would we gain, either percentage wise or dollars wise? Would we increase our percentage of a new product or new product design if we had better information? How much should we be willing to pay for that? Well, we can calculate that out by calculating the multiplying the probability assigned to each of the states of nature by the largest payoff and then summing those up. We can figure out how much we'd be willing to pay for that additional information, for that additional time. Okay, so that's kind of an important concept as well. It does bring us right back to Bayes' theorem. This is, again, if you recall, Bayes' theorem is really about prior probabilities. We get some sort of new information, and then we have a post probability based upon that new information that's come into play. Okay, and it provides, Bayes' theorem is going to provide a means for revising that probability based upon new information. So here's an example. Consider a manufacturing firm receives a shipment of parts from two suppliers. Currently, 65% of the parts purchased by the company come from supplier 1 and the remaining 35% from supplier 2. So we get the bulk from supplier 1 and whatever else is left over, 35%, we get from supplier 2. The quality of purchased parts varies from the source of supplier. Historical data suggests that the quality ratings of the two suppliers differ. So A is the event that the parts come from supplier 1, and A2 is the event that the part is from supplier 2. Again, purchasing, we know that the probability of A1 that it's coming from supplier 1 is 65%. The probability of A2 that it's coming from supplier 2 is 35%. But here, supplier 1 provides good parts 98% of the time and bad parts 2% of the time. Supplier 2 provides good parts 95% and bad parts 5% of the time. Hence, probably why we have this 65-35 split, okay? So, from this information, we know that the probability of it being a good part, given that it's from supplier 1, is 98% probability, okay? And then the probability of a bad part, given that it is from supplier 2, is supplier 1 is 2%. The probability of a good part, given that it's from supplier 2, is 95%. The probability of a bad part, given the supplier 2, is 5%. Okay, so from here we can create a decision tree, and let us, again, a couple things I want you to know right off the bat. When we add these up vertically, each of these columns, they have to equal 1. Okay, they have to equal 1 all the way down. And what we do is we multiply across. We are multiplying across. So again, this is how we got to our numbers. So each of these here, each of these will equal to 1 for us. Okay. And so what we do is we simply say, okay, now suppose that the parts from two suppliers were used in the firm's manufacturing process, and that a machine breaks down because it attempts to process a bad part. To find the posterior probability, or the probability after the event has occurred, we need to use Bayes' theorem. Now, this theorem looks nasty, but it's really not that bad. So let's break it down here for us. Given our information here, the probability of A, right, is the probability the part comes from A is 0.35. And so we just simply plug in our numbers, right? We've got our 0.65 times 0.02, and then the probability that came from A again, and that it's bad when it came from A is 0.2. We work all of these numbers in here, and we get to a 0.4262. Okay, so since we know that that needs to add up together for us here, we know that this is going to be the one minus that, right? The fact that the probability that came from supplier two, given that it's bad, is going to be our 78.38%. So here it is, right? The probability that it came from one and it's bad is only 42%. Therefore, the probability that came from supplier two and it's bad is 57%. Okay? So even though, let's go back here a step, even though we get 65% of our parts from supplier one, right? The majority come from supplier one, but if it's bad because the supplier two provides us bad parts at 95% versus 98%, there's a greater likelihood that this bad defective part actually came from supplier two. All right, and we can do the exact same thing in a tabular approach as well. So sometimes this is easier for folks than the tree, so let's just look through this. Again, we've got a probability 65-35, supplier one, supplier two parts. The conditional probability that it was bad, well, supplier one only gives us bad parts 2% of the time, and supplier two gives us bad parts 5% of the time. So then we add in the joint probabilities, okay? And so all we're doing is we're simply multiplying the percentage of parts that are bad from supplier one, and we get to 1.30. And then from supplier two, 35% of the parts and 5% of those are bad, we get to 0.0175. So from there, if we want to figure out those same percentages, we can look at it this way. We can simply add this up, this 0.0305, and we'll divide both of these by that number. We'll divide the 0.0130 divided by 0.0305, and we'll see that play out here for us. Here it is, where we take 0.0130 divided by 0.0305, and we get to our 42% and our 57%. Again, indicating we have a better than 50% chance that the part came from supplier 2, even though supplier 2 is only providing us 35% of our parts. Okay, so again, decision trees and decision analysis and expected values and profitability tables, all of these help us to quantify or put a number to some of the complex decisions that we have to make in our daily lives and in business. Keep in mind events and acts, right? The differences between those two things, and you should be set to go.